Great. Welcome, everybody, to this special robotics seminar just before the semester start. We have the great pleasure of receiving today Eric Feron, who's a professor in electrical and computer mechanical engineering at KAUST, King Abdullah University of Science and Technology in Saudi Arabia. Feron has actually been doing research and teaching quite all over the place, including Georgia Tech, where we cross paths shortly.
Yeah. You on the way out, me on the way in.
Correct. MIT and other several institutions over in France. Eric Feron's interests include fundamental concepts in control system optimization, computer science to address problems in aerospace and transportation systems, robotics, software system certification, and human-machine interactions. He's been very prolific, published 3 books and several research papers on the area, and started 3 companies. So he's a fellow from the American Institute of Aeronautics and Astronautics, a private pilot, and an offshore sailor. We had quite a bit of fun learning about those experiences earlier today. So he's going to be talking to us about Ariadne, and without further ado, I'm going to let him do the honors.
Thank you very much, Nancy, for this nice introduction. And it's always a true pleasure to be spending my summer in the United States and take advantage of my mobile home on the water to actually circle around, the nicest place, such as University of Maryland. And it's even better when I send a little message, I get, yeah, please, you're welcome, come on in. So I really thank you for your welcome. Hi, everyone. It's very nice seeing you too. So you're all graduate students here? Yes? Anybody online?
We have quite a bit. They typically communicate via email, so it's a little.
They communicate via email. Okay, so I will be looking for your emails, so I'm an aerospace person. I started doing that when I was literally around 1990, when I started my PhD at Stanford University, and now. I arrived at KAUST and they don't have an aerospace department. So I tried to say, okay, so what does it mean to be aerospace? And how many aerospace are there here? 1, 2, 3, 4. Okay. What are the other majors here?
Computer science.
Computer science? ECE? Mechanical. All right. So I think and I claim that being an aerospace person is being all of the above. So that's why now I'm a professor of electrical, computer, and mechanical engineering. Okay. You need to know your fluid dynamics. You need to know your computers, okay, both architectures and programming. And you need to know computer science, not as much programming as science, because your programs cannot fail, okay? And of course, electrical, because there is always some wiring involved. And as you know, some of you who have been following at least the advanced air mobility efforts, well, it looks like the whole world is going to turn electric soon, including the flying world. So I have a number of topics I can talk about. And what I wanted was to find a topic where I wouldn't have to cover a single equation. You would think it's for your own good, no, it's for my own good, because I'm getting older and I usually trip the line when I try and do equations. So I decided to ban equations from my presentations. That said, the topic, I think, is fun. It is, so how do you do provable safety with unreliable components? This is a topic that has been, at the same time, known forever and not formalized all the time. So it's one of these topics which comes and goes, and it reformalizes itself from time to time. And there are like several ways to look at it. Okay, the core message that I want to say is when you're in a mission, when you're flying, when you're doing something, always work with one plan B ahead of you. Okay, so there are other ways of thinking about it. It's like, for example, you have an autonomous system. Who works on autonomous systems here? Yeah, quite a few, right? It's like, well, if your system is autonomous and so smart, when you tell them not only how to do the mission, but also how to get out of it, okay? It's the same thing, make it work a little harder, Okay, and if it cannot get you out of it, then start wondering, what should I do? And so that said, I will be covering some general things about safety first and systems engineering. I will talk about malfunctioning algorithms, whether they are in computers or in our own human heads. And then I will talk about what I call the Ariadne principle, but it has other names, including runtime assurance and things like that. And then I will talk about some embodiments, past, present, and future. So before I do that, let's do a little detour by Saudi Arabia. This is KAUST, okay? It is a, how should I call it, a sea resort with a university problem, okay? You see, this is the Red Sea, okay? It is, believe me, the most beautiful sea in the world. It is absolutely beautiful. It's so salty that you don't have to move your arms to float. You float. Period. Nevertheless, it's not that salty such that it can sustain an incredible amount of life. You see, Saudi, you think of it as what? When you say Saudi, okay, you think about oil, then what else?
Desert.
Huh?
Desert.
Desert, right? So it's a pretty dull country, right? Unlike here, Maryland, you know, it's a beautiful part of the country, right? It's all green, there's tons of stuff, nice building. So Maryland is pretty nice. Now, if you go underwater in the Chesapeake Bay, it's pretty dull. In Saudi, it's the opposite. Okay, above the ground is pretty dull, but underwater is like the most magnificent garden you can imagine. They have more corals than pretty much anywhere else in the world, especially because anywhere else in the world, they're like shrinking super fast. And as we know, by just looking at the news. But otherwise, so the university is made out of a number of buildings. Okay, by the way, this is the great, there is a mosque, okay? That's one of the, I don't know how many mosques there are, but that's the biggest one. Okay, so there are like 1, 2, 3, 4, 5, 6, 7, 8, 9 research buildings. Okay, that building, by the way, is the ocean engineering or the marine facility building. And usually right next to it here, there are a bunch of very, very expensive research vessels. I was on one of them. Frankly, you know, when doing research on the Red Sea on a boat, feels very much like just a cruise. And for the record, so another view you have is from the building. This is the view from my office, okay? And what you see here is, well, they couldn't help. There's a monument there. It's a nice monument. It's actually pretty nice. I even was able to run like a little bit of physics experiments with it. But these are the student residents. And as you see, some of them are right above the water. And what do you do if your balcony overlooks the water? What do you do?
Fishing.
You fish, exactly. So that's what they do.
I was at KAUST.
Oh, you were? So you went fishing. What took you to KAUST?
I was actually part of RISC, so I admired that you kept the same logo. I actually just left before you joined, and I was working with Professor Jeff Gemma, so.
And you left to come here?
Yes.
Okay, welcome a newcomer. You already talked? Okay, very good.
So while you were describing the story, I was just reliving the moment.
So,
over again.
how many lies have I said so far?
I would say nothing. So
Nothing, right?
That's pretty accurate.
I mean, you know, and the reefs are absolutely beautiful, aren't they?
Absolutely.
Right? So, that is one of the few restaurants that are around the place. And you see over there, everything that's blue is sea, everything that's light blue is coral reefs, pretty much. Okay? And okay, so of course, you know, a slide cannot show you the temperature, but as soon as you're on the sea, it's perfect.
Yes.
You know, on land, it's very humid, very hot, and you have to get used to it. But of course, on the sea, then it's like anywhere else on Earth, which is, in my opinion, paradise. So that's the first view that I want to give you of Saudi. Okay, and here is a second view, which is the RISC lab. Look, we are now about 30 people. Yep. We're 2 professors instead of 1. So Professor Shamma, who now teaches at the University of Illinois Urbana-Champaign in the Department of Systems and Industrial Engineering, was the director of this lab. He named it. the Robotics Intelligence Systems and Control Lab. Okay, and you recognize at least a couple of faces in there. How about the tall guy there, Bilal?
Yeah, I remember.
Right, Bilal. Okay, he still cracks the biggest jokes around. So, and then there are like, so it's about 25 people. You know, there are like you know, people of different backgrounds. You know, of course, you can recognize that there is quite a few Saudi people. Okay, but we have people from Kazakhstan. Okay, guess what country? Hold on. Let's see. What country is this person from? Make a guess. I'm going to make it easier for you. His name is Kim.
South Korea.
Kazakhstan. Okay. So, and that's what happened. Okay. There is a, are you Korean? Yeah. No. Well, there was a, I mean, you learn a lot about the world when you go there, including that lots of Korean people got displaced into Kazakhstan. And so his first name is Anton. So there are people from Kazakhstan, people from Pakistan, Saudi, Ukraine. I forgot where the Russian one is hiding, but you know, we have like a ton of countries. This is an F-15 experimental flight testing pilot. Next time you see a woman wearing, you know, the traditional scarf and overall garment, watch out for what you're going to ask and think. Okay? And Mexico, where do you think that girl is from? So this is Iswan. She comes from Taiwan. So you see, diversity, I think you probably recognize. Where were you from?
Pakistan.
Pakistan. See, so chaos constitutes, I mean, I think a nice hop from Pakistan to the rest of the world, even though it's not necessarily easy for Pakistani people to get into chaos in the first place. So you were a gold medalist?
I was actually.
Yes, I mean, that's the only reason you managed to get in. No, I mean, you know, the university tries and maintain like an extremely international background, and you know, I mean, short of being a gold medalist, you Pakistani people cannot come over. Period. It's that simple. Okay, and but then eventually, welcome here, and so we are two professors. There is myself, and there is Professor Shinkyu Park, who graduated from Maryland. Exactly. Okay, with Nuno Martins, right? By the way, I'm Nuno's uncle. I mean, academic uncle. I was on his committee. So, you know, it all stays in the family somehow. So here's one thing that, for those of you who haven't heard about chaos before, especially if you are sort of not necessarily from the Middle East, okay, is this. Have you ever seen this book? Huh?
Yes.
Yes. What does it say?
It's like you have two systems in your mind. One is fast and one is slow, and you're thinking of.
Yes. So why does it relate to Saudi Arabia?
The author is from Saudi Arabia.
Huh?
I mean, the author is from.
Oh no, he's not from Saudi Arabia. No. He's from Israel.
Yeah, he's teaching in Israel.
Yes, and at Princeton.
Yeah.
So now, here's the story. Daniel Kahneman wrote this book, and the entire book has base rule behind it. And what does it say? It says that people, in general, when they face an event, they pay too much attention to what they see, the observation, versus what they know, which is the prior. And so they completely overweight what they see compared with what they know. And often that leads them to making stupid decisions. Okay? That gets them into thinking against rational. They have reasonings that look rational, but they're in fact they're counter-rational. Okay? because they overweight their immediate observation against their prior. Okay. Now, what I'm saying, and the reason I put this slide here, this book here, is because as far as Saudi is concerned, you should be doing the opposite, which is you should completely forget about the prior and then see for yourself. Because in much of this country, the prior about Saudi Arabia is completely wrong. The mean is completely wrong. The variance, the standard distribution, the standard deviation is completely wrong. Okay? Basically, if you read the Washington Post, your prior is as good as the restroom next door. And I'm not talking about the ladies' restroom. I'm talking about the guys' restroom. Okay? Just come and see for yourself, and you'll get a much better idea. So trust the observation, don't trust the prior. Okay? So that said, let me go back to the talk here and talk a little bit about safety and systems engineering. So my talk is going to be about safety, and it is about how to do things carefully, how to do things in a way that they don't fail. And so there are several ways that we learn about this. In the world of aerospace, which forms a kind of a reference in terms of safety. Are you afraid to fly? No. Are you afraid to fly? Are you afraid to fly? Are you afraid to fly? No. Anybody afraid to fly? How about driving?
A little bit.
A little more, right? How about motorcycles?
Never tried one.
Never tried one, so you didn't even think about it. Okay. How about you?
It's fine. If you practice, it's fine.
Okay. But you're more comfortable on the motorcycle or flying?
Maybe fly.
Okay. So the idea is we fly, and we fly without worry because the system is completely safe. Okay? And as people say, fail safe. That's all I'm talking about. Fail safe stuff. Okay? And for that, aerospace has solid design principles, system design principles. Are there courses in systems engineering here? Yes. Okay. You know what? This is sort of one of the most frustrating subjects I know, because there's no theory for it, but if you don't know it, you shouldn't go into aerospace. Okay? Because there are very disciplined processes. There are very good tools for software, okay, and for hardware. You don't do your software in the way you program an app, okay, and you don't do your hardware like it's on that that perfectly honest Apple computer. You have certain software design principles, certain architecture design principles, okay, that prevent you against failures. You have regulations and reference documents. Who knows what RTCA means, for example? RTCA, you heard about this? SAE, have you heard about this? Yes? So RTCA is Radio Technical Commission for Aeronautics. SAE is Society for Automotive Engineers. And you know what they do? They write tons and tons and tons of documents that explain how things should be done when you build an aircraft, when you build a car, when you put together a building, okay? And most of these regulations have to do with safety, okay? But they've never been as developed as for aerospace, okay? It's because there are these tons of documents available that you can fly safely for every catastrophe there was, whether it's an engine failure or a door like opening up during flight, or the landing gear that refuses to deploy, or two aircraft colliding with each other. Each time there is another one of these documents, okay? And that started in 1903 and it goes on today. So you also have technologies. When you design a system, you have like requirements tracing, fault tree analysis, failure mode and effect analysis, static software analysis, simulation testing, safety by design. I like this one. That's what I'm going to talk about, okay? Static software analysis, also called formal methods, okay? And that's where you actually meet in software the equivalent of Lyapunov functions, the name ranking functions, okay, to formally analyze software and prove, for example, your program is going to terminate. Okay, and then you have education. If you're interested, I offer an online course via Udacity on cyber-physical system design and analysis. It's on Udacity, but it's part of the Georgia Tech Online Master of Science in Computer Science. It basically talks about that kind of stuff. It's now offered at CAUST, online. So I don't go to the lectures. The TA goes, okay? You can imagine the face of the leadership when they say, what, it's online? Say, of course it's online. It's never meant to be any other way. Maybe I can take it off. Say, don't. So I'm good. But I teach it on top of my usual course load. So I'm the only professor who taught 4 courses last year. 2 of them were online. So this is it, okay? This is the general framework that we're working with. And then, well, now we're facing some new things. We have a software revolution coming, and sometimes overwhelming us, and sometimes we wonder if the wave has passed us and then goes further towards the horizon and leaves us wondering, excuse me, what happened? And, you know, we talk about new sensory capabilities, we talk about new algorithms for, and models for behavior planning, okay? And some of them are like at random, what is it, RTs, okay? How do you say, random? Rapidly exploring random trees. Rapidly exploring random trees, okay? You have like all sorts of randomized algorithms in general. And then some people say, oh, let me put that on my autonomous car. And the people are like, ah! And what happens if the thing fails? Okay, I say, well, well, actually, we can do something about it, okay? But, you know, you see all these algorithms, you see like reinforcement learning. My algorithm is going to figure out the path towards the truth, right? AI is sort of this new crystal ball that will tell us everything so we don't have to do it ourselves, all right? And so these are, you know, at the same time, very, very interesting, very attractive, but from the viewpoint of people whose life has been spent working, say, in the Department of Transportation or the FAA building. Who's been to the FAA building? You know the address? 800 Independence Avenue. Okay, so all the aero, you go there. Just to check it out. It's good, it's covered with marble. Okay, I mean, the container is beautiful. Now, the contents you will judge by yourself. But it's right there next to the Smithsonian. So, and not far away. So it's really not far away. Okay, and NASA is hidden behind the NASA headquarters. Okay, so I'm not going to talk about sensing. I'm not going to talk about perception, at least not yet. Okay, because sensing and perception, well, to face it, they are the really hard problems, and I specialize in easy problems, okay? Hard problems, I leave it for the others, you know, because I want to work on the easy ones, and especially if I can still deliver some kind of message, okay, useful message. So looking at planning, behavior planning, and things along these lines, well, we still have questions about, are we planning okay, or are we planning for failure? It turns out we can plan for failures. Okay, what if the algorithm malfunctions? So the example I'm going to pick is a very old example, whereby the algorithm was running in somebody else's brain. Okay, here's the story. So there was a team of, I think it was basketball players from Kansas who wanted to run a competition against a team from Utah. For that, they chartered a propeller aircraft back in 1970, and they flew with that aircraft, privately chartered aircraft, from Wichita to Utah. And the trip went as follows. The pilot said, we're going to make a stopover in Denver to refuel. And then we're going to take the scenic route from Denver to Utah. And decided to use that valley, okay, which is a little bit north of Denver, if I remember well. And they said, we're going to fly inside the valley, up and up and up and up and up and up, and up along the valley, okay? And the passengers are going to have like spectacular views of the mountains around them. We're going to fly even lower than the mountains. And they're going to see what they're going to see. And they saw what they didn't want to see, which is that the mountains climbed up slowly. The airplane climbed up. They were in the valley. And the valley stopped. A wall in front of them. What happened? Well, so they faced that situation, okay? They faced that situation. They faced the lowland. They faced that circus where there was mountains everywhere. And they couldn't go anywhere. That's it. You know, it's when you get into a dead end. It's like, dead end. So what do you do when you hit a dead end?
Well, you can turn around.
Yeah, you turn around, if you can, right? Sometimes it takes work, right? And so, I mean, with a car, you can stop, back, move forward, back. This was a propeller airplane. It doesn't do that, right? It needs a certain radius to make a turnaround, and the radius was too large. It was too low. It could not pass. It was 11,000 feet instead of 11,990 feet. So it was 990 feet lower than the lowest point across towards safety. So, well, they tried their best, and that's what happened. So, typical bad planning. Okay, typical bad planning, in the sense that I mean, you can say it in several ways. You can formalize it or not. You know, you can talk about viability kernel. Who knows what a viability kernel is? Who wants me to switch to the language of viability kernels? Nobody? Okay, good. So we keep talking about these kind of things and say it was bad planning, in the sense that the pilot was too short-sighted. They wanted to go to the valley, but they had not planned any backup solution. They did not think, how do I get out of this thing? Right? They did not think about it. And at some point, they got trapped. Okay? So basically, they were doomed pretty much as soon as they entered the valley. As soon as they entered the valley, they were toast. Okay? And but they didn't know they would die, but they were already, like, you know, the clock was already ticking. So what's the iron thread? Well, I call it, it works for transportation, but it works for lots of the things, which is that you should never do anything, any operation, without thinking about what to do if the thing doesn't work well. So you should always think ahead and say, I'm going to fly. I have to figure out, I have to know where I'm going to land if I lose the engine. I'm going to have, you know, in an airplane with more pilots, you know, if one of the pilots dies, the other is able to fly the airplane, okay? Or otherwise, find something, all right? And this is easier said than done, okay? And also keeping it constantly in your mind, you know, and, you know, so I have to take care of the pilot dying. I have to take care of the engine running out. I have to take care of my ability to land anywhere I am. I have to take care of what happens if I lose a control surface. I have to think of, well, literally all these things, okay? For every one of these things, I have to have a plan B, okay? And easier said than done. So, of course, there's nothing here, nothing deep, no equation, no whatever. Okay, it just says, think before you start doing something, pretty much. So I call it a thread. And the reason why I call it a thread, and it's attached to the word Ariadne, is who's heard about the Ariadne thread? Nobody? Okay, so here is Ariadne. Ariadne was the daughter of a king of Crete. Okay, and what did she do? Well, she fell in love with a guy named Theseus, who had been brought to Crete in order to rid the island of a monster named the Minotaur. Okay, this fellow here. Oops, sorry. And let me unfold my little. Where is that? I had a little.
Center screen.
That's what I was looking for. Okay, so thank you. So this guy was brought in to kill this Minotaur. Okay, and it doesn't work. This is the Minotaur, half human, half bull. Okay, I let you read the rest of it. The Greek mythology is an orgy. Okay, when you look at it, say, I can't believe, in many civilizations, the gods represent sort of an ideal of humanity. It's like the god is like the perfect version of the human. In the Greek mythology, gods are like the worst of what the humans can think of. Okay, and they all have a name, and they're all gods, and they're all uglier in terms of behavior, one than the other. So this guy is sent to kill this guy. The guy is stuck in a maze that you cannot get out of because he's too dangerous. So you put him in a maze, and then he's wandering there forever. Who designed the maze? Deadalus. You heard about Deadalus? The inventor of flight. The first guy to fly successfully from Crete to Greece. His son didn't have such a good fate. What's his name?
Icarus?
Icarus, exactly. Icarus flew, but he flew too close to the sun, and his wings melted. So Deadalus, who was a definitely smart guy, started by building this labyrinth, which is that maze. And there was a problem, because as soon as you enter the maze, you get lost, and you cannot get out of it. Okay? So, going back to Ariadne, she said, let me give a spool of thread to my lover so that he carries the spool with him and unrolls the spool while Ariadne attached one end of the thread to the entrance of the labyrinth. And then when he's done with his job killing the Minotaur, he can just go back and find the exit by just following the thread. Okay? So that's why it's named Ariadne thread. And it's used in not only in mythology or in engineering, but it's also used as a common word for like what you would call like a dominant theme. Like for example, an Ariadne thread was, a dominant theme that people best meet when they are face to face. And ever since the COVID, it's all gone out the window, of course. Okay, but nobody says what happened. Well, we know one possible end that happened, which is, yes, Theseus killed the Minotaur and made his way out of the labyrinth. But nobody says what would have happened if he had run out of thread before he finds the Minotaur. Right? So what you do, if you run out of thread before you find the Minotaur, and you're in a place where you basically get lost, if you don't have a lead back to the exit, what do you choose?
Go back.
You go back, right? Okay. Remind me of this joke about the French people, What do the French people do when they are attacked? They're like, we surrender! So, how about you? You go back?
I mean, that's one option, but you could just cut the thread and fight.
Yes, but but that means you get rid of the thread, right? So if you run out of thread, so you still go and you say, okay, forget about the thread?
Yeah, if you have a demon to kill, maybe. That's an option. I mean, I wouldn't do that probably.
Yeah. Well, yeah, it creates serious moral problems, right? Especially if you said you would do it, right? What would you do?
Go back.
Go back, okay? So it is, because we're talking about civilian applications, you know, we're not that brave, okay? And if we are out of thread, okay, we should go back. Well, if you run out of plan Bs, you should trigger the alarm and go back. Not when you're in trouble, but when you are out of options out. It's that simple. Okay? So, how does this thing work? Well, it works pretty well. There's another version. You know, you've heard about this guy, the little kid who like drops little stones behind him, and because his parents are trying to lose them, right? So he leaves the little stones, but at some point he runs out of stones. I don't know how he managed to run out of stones, you know, out of pebbles. I mean, pebbles are everywhere. Okay, so he ran out of pebbles. So what did he put instead?
Breadcrumbs.
Huh? Breadcrumbs, right? And you know what happened, right? Well, the system didn't work anymore. When, you know, he was putting the breadcrumbs behind him. The parents lost the kids. He told the other, "Oh, I have a plan. I have a back plan to take us back." And I said, "Bummer, the birds ate the crumbs." So you know, the plan B didn't work as well as expected. But anyway, so since Ariadne presumably lived before the Middle Ages, I claim Ariadne is the inventor of the backup plan. And it works. You know, when you fly general aviation, we were talking about it with Professor Odi before. You know, what they tell you is when you fly as a pilot, you know, flying like a little Cessna aircraft, they tell you after you take off, okay, start looking for landing spots. They say, why? They say, start looking for landing spots. And they say, why? And then they turn off the engine and say, now, where do you go? And like, oh, say, okay, where's the landing spot? So they tell you, you should always be looking for a landing spot. Okay, that's nearby. And they tell you to monitor highways, although I'm always uncomfortable with highways, you know, but also golf courses, you know, all these places that are like relatively well taken care of, maybe fields, in such a way that in case your engine quits, at least you know where to land. Okay, and it's already planned in your head, which means that if you decide to fly overseas, over water, or over forests, you should know very well what you're talking about. Because if your engine quits then, well, then what, right? If your engine quits, what do you do? Well, that's where you wish you had flown earlier. Altitude in an aircraft is like money in the bank. Okay, the more you have, the better you feel. All right? And then in the forest, of course, it's well known as well. And there's been interesting cases of 737s getting lost over the Amazon forest. And basically, when they realized that they were in the middle of the Amazon forest, there was nowhere to land, and they crashed. So this is what you do when you fly over water. Okay, you do this thing, this Plan B stuff. Okay, when you fly from, say, New York to Paris, you fly carefully, meaning that you always keep in sight an alternate landing spot. Okay, so I claim it's not that you aim at Paris, you aim at the next landing spot that can take care of you in case, well, usually engine failures, in case an engine fails. You see, engine reliability has been going up and up and up and up and up. Okay, and for example, it was nowhere close what it is today in 1970. And that is one of the very few reasons why the 707 had how many engines? 4. How many aircraft have 4 engines today? How many? How many aircraft types?
I think A380 has.
That's it. Yes, for large transport, A380. Everybody else is at
2 engines.
2 engines. Okay. Now, do you remember a period where there were 3 engines?
Yes.
Okay. So that was when they figured out, hey, I can do with 3 engines, I can be just reliable enough that I can cross the Atlantic Ocean without worrying about what happens when I lose 1 engine. But then at some point, people wanted to cross the Atlantic Ocean with airplanes with 2 engines, and the engines were not that reliable. So what did they do? They said, okay, you're authorized to fly across the Atlantic Ocean, but always stay within acceptable distance to an alternate airport. And then that distance was measured in minutes. So there was like the 60 minutes distance, there was the 90 minutes distance, there was the 120 minutes distance, and there is now the 180 minutes distance. What does that mean? 60-minute distance, you have to stay within 60 minutes of an okay airport. Then, so that means that you have to stay close to land. 90 minutes, you can be further away from land, because now all you need is to stay within 90 minutes of an airport. Okay? And then, and so on and so forth. Okay? You know what these are? They are the diameter of the, the area you can cover in 90 minutes to that airport. In math, we call them level sets. Okay? Reachable sets. Okay? And it's hard to say, but behind the concept of what's called ETOPS, extended twin engine operations, okay, there are Lyapunov functions. Okay? Now I'll show you more about this, but what it means is, you always stay within the within reachability, or you always keep at least 1 airport within your reachable set. Even when your reachable set is that of having only 1 engine, not 2. Okay? So there you are, flying from your origin to destination, and always keeping up that backup option. And what that means is that in this particular case, you have to fly within the union of those disks. Okay? You cannot fly what could look like direct. Okay? You cannot fly here. You're not allowed to. Okay? Why? Because you don't have a backup. So you have to fly here. Now, over time, it's becoming more and more relaxed, but it still is happening. And that explains to you why this airport in Greenland can accept a 747. Okay? That completely lost area in Newfoundland, Gander Airport, a grand total of probably like what? Maybe 1,000 inhabitants, has a runway that can accept Air Force One. Okay? It's because it's a backup airport. And guess what? Sometimes people going to Paris or from Paris going to New York find themselves landing in Gander. Okay? And then, it's like, it's like Christmas for the local population, because suddenly they have this inflow of tourists, okay, and it's like party time. Okay, finally some people coming and seeing us. So in air traffic control, there are other things of this kind, okay, and that I think explain a lot about air traffic control and why the sky is empty. One of the things that I've noticed is air traffic control will never allow you to fly without the option of at some point stopping. Now, stopping for an aircraft means to go circles, okay? Normally, they will not let you fly unless you can, at any point, go do circles, okay? So that your trajectory, say, from here to there, okay, is not a trajectory from here to here to there. It's a trajectory from here to there. And then when you get there, and you've thought about it carefully enough, if you have the next trajectory from here to there ready, then you forget about this one and you go this one, okay? And then it goes on. If you keep flying, and if here you cannot come up with anything else to move forward that ends up in a circle, then you go there, okay? And you start circling, okay? And you exercise your option. I'll tell you more about this. Fortunately, in this case, you can do it, okay, go, all right? But you always have short-term horizon and a long-term horizon. And your short-term horizon is actually a safe path. It's a safe path that you eventually give up because you have the next one available, all right? And of course, you know, you have to think about the logic about how to make this work, but it works. It works. And not only it works, but it works well. Now, I talked to my F-15 pilot, you know, the woman who was dressed using the traditional Muslim attire and or Middle Eastern attire, and showed me, I hate doing racetracks. Says, when I do a racetrack, that's when I start panicking. Air traffic control asks people to do racetracks. You know why?
Do they have time to come up with plans? Or?
Well, says when the airport is congested, they have to stop the aircraft because too many are trying to land, so they go do racetracks. And the pilots are like, I hate racetracks, okay? Because I don't know when I'm going to have to, when they're going to pull me back on my path. And in the meantime, I burn fuel. So what they do is they say, okay, for the racetrack, but can you give me an alternate airport as well so that when I run out of fuel, I have the eventual ultimate backup plan, which is I land, I stop, and then I stop worrying.
Is that bad weather?
So I just said, yeah, the case of bad weather or something like that, you know, and maybe the bad weather closes, and in which case, well, you know, you can at least stop and think a little bit about what's coming next. So there is all this is sort of built implicitly in the minds of air traffic controllers. They always have that in mind. Okay, not only what you're going to do now, but what should we think about in case we have a problem, okay? And these racetracks happen, each time there is a storm over New York, there are racetracks happening somewhere else. Because all the aircraft aiming for New York suddenly create like this huge bottleneck, this huge traffic jam, and they have to slow down the aircraft. So bloop, bloop, bloop. You can start seeing the, you can find it on the web, you know, examples of how eventually, because there is a storm over New York, you know, the traffic all the way up to above Chicago is on a racetrack waiting for the storm to stop over New York. We did an implementation of that was a long time ago in 2003. And what we did is we were planning the path of an unmanned aerial vehicle. That's called the UCAV. It was one of the fancy things designed by Boeing. I mean, I'm just kidding. They did not give us this one. They gave us that old clunker. It's a T-33, okay, coming out into production in 1948, okay? And they promised us that it was equipped with the same avionics as the JUCAS, okay? So they gave us that old clunker, and but you know, we were rather happy. Even the clunker of that size, you know, which doesn't fit in this room, you know, it was nice to do experiments with. And then there was an F-15 that was sort of, you know, remotely interacting with the clunker, and they said, okay, do path planning with this. And we did exactly what I showed in the previous slide, which is we told this machine to plan its trajectory, but we were using a technology that you probably know coming from operations research named mixed integer programming. Have you heard about that? Mixed integer programming? Okay, so the one thing it does is it does it well, but when it doesn't do it well, it does it real bad. Like it returns like, sorry, I found nothing. Okay, so we needed to protect the unmanned vehicle against itself. So that's where I said, we told this vehicle, think a little more and not only plan a path, but find us at the end of this path a racetrack, okay? And then we'll follow that path because we know there is a racetrack at the end, okay? And when we started implementing this thing, there were racetracks everywhere. the trajectory optimizer was so badly implemented that literally, like, the trajectory was littered with racetracks. And then, as we started understanding the implementation better and better, the racetrack started like spacing out, and sometimes we would enter a racetrack, and then the algorithm would say, wait, let me think again, okay? But in the meantime, keep doing your racetrack, and then boom, it would come up with a solution and say, okay, I can take you to the next stop, and then on the next waypoint, and then it would do that, and then eventually, there was no racetrack anymore until the actual flight test, and then things started all over again, because of course, real life is never like you wish it were in theory, right? And so racetracks again, and the pilots send a little message, say, well, this was happening at Edwards Air Force Base. You know where that is? One of the meccas of flying, okay? That's where the Air Force tests all of its naval aircraft. That's where you could fly, and can still fly, see B-2s flying. I was lucky enough to see the SR-71 flying and everything. It's north of Los Angeles. And the pilot told us, it's so nice, at least with our experiment, we did not end up over Los Angeles. So they were glad there were racetracks. And then I started thinking back and say, wait a minute, I must have been thinking about this before. And then I remember an old paper that we wrote with a fellow named Mark McConney, who was pretty much my first PhD student. We were co-supervising him, Munzer Dahle, and I. And we're thinking, oh, we're trying to control nonlinear systems. And we're thinking, okay, how do we control nonlinear systems with guarantees? Nonlinear systems and guarantees, it's kind of often a tough proposal. I say, okay, so what we're going to do is we're going to take a bunch of equilibria, all the possible equilibria, the equilibrium manifold of the system. You have a number of equilibria, all you have is to adjust the control to the proper value, right? And we say, we're going to take out that manifold, and instead of going too crazy in the state space, we're going to fly. We're going to start here, and if we want to go from here to there, what we're going to do is we're going to start by going towards this point, which is an equilibrium. And we have a Lyapunov function around it. I told you the Lyapunov functions were coming. And then we're going to go there. And by the way, as soon as we enter within the guaranteed domain of stability of that equilibrium, we're going to switch from flying towards this equilibrium to the next equilibrium. Okay? And then when we run out of this, we're going to, when we keep going, hold on a second. Sorry for this. When we get into a domain of attraction of that equilibrium, okay, indicated by this level set, then we're going to switch, and then we're going to go there. So eventually we had reinvented extended twin engine operations, but there it's an arbitrary state space, and it's for system. And that makes the difference between publishing a paper in an AIAA journal versus the IEEE transactions on automatic control. Okay, you say, you abstract everything to an arbitrary state space, and suddenly you make it to transactions. Okay? Whereas the other thing, like twin engine operations, people are like, come on, no, it's the same stuff. But one is with equations, one is without the equations, and I thought I would spare you the equations. And then I started scratching my head and say, not so long after we did this, there was this guy. So this is sort of the demo. Of course, it's not an airplane, it's a plant. And I remember this picture. And this picture was done by Emilio Fazzoli. And it was about path planning. And it's virtually about the same as what I showed you before. But he said, you know what? I can mix this idea of always having safety and being able to at least stop an equilibrium together with path planning. Here's how it went. So you start from an origin here. You add 0 speed. Okay? So you have two coordinates and then say velocity, and say that's all your state space. Okay, and you want to go from here to there. Okay, so what's the principle of RT? It is or you're going to start paving your state space with, well, more precise, your configuration space with dots, right? And then you got to connect the dots and eventually build a tree that takes you from origin to destination. But the problem is, you want to add velocity things. So what he imagined was, okay, so here's what I'm going to do. I'm going to pave my state space with dots, but those are not dots in the state space, they're in the configuration space. And then I'm going to say, plan a trajectory from here to there, where I stop there. Okay? So it's like driving a car, okay, and having an objective, and your objective is to be stopped. And as you fly, or as you drive, keep thinking about the next spot. Keep sampling the configuration space. And maybe you come up with something which is a little closer to our target. So what do you do? Well, of course, you don't go to that stop, okay? You keep going and driving along. And as you keep driving along, of course, you keep thinking ahead and creating new samples until one of them is sufficiently close to the target, and then you're done. So you pave your state space or your configuration space with equilibria that you always aim at and never get to. Because you always keep thinking, oh, while I was driving towards this thing, I already have other intermediate waypoints that I can use, because they themselves can lead me to a more stable, steady state condition, which is on the ground, stopped, or, of course, you could imagine it can be also one of these circles, okay? And so I told him, this is what you are doing. By the way, this is not very different from that, okay? The only difference is that here we were probably talking about a predetermined definition of equilibria, and here the distribution of equilibria is actually chosen at random using some of the standard sampling-based algorithms. Okay. So that's Emilio. So looks like that's what we're doing all along. You say, oh yeah, pretty much. I say, oh, and by the way, in my company named Autonomy, this philosophy of always starting something with an endpoint which is satisfactory, even though we never get to it, but we keep going, is the foundation of the entire software stack that runs the autonomous cars, from the lowest level all the way to the vehicle guidance. Okay? So, I just couldn't resist mentioning that. In a probabilistic framework, you can do that too. How do you fly? And here's another thing that you do. How do you fly from Paris to New York? Do you have enough fuel to fly to New York? The answer is most of the time. So you take off from Paris and you go to New York without knowing if you actually do have enough fuel. Why do airlines underfuel their aircraft? Weight, right? The more fuel you add, the more fuel you need, the more fuel you add. I mean, sort of, you can get into, I mean, there is only a certain distance before which you cannot go. Okay? So it's expensive. And the airlines would very much like to fly you from Paris to New York at the lowest possible cost, so they can pass on the savings to you or keep the benefits for themselves, which is not the case. Airlines are they're like ultimate money losers. So here's what they do. They say, okay, so I'm going to fuel up, and there is 99 out of 100 chances I will reach New York. So they don't file a flight plan to go to New York, because you're not allowed to file a flight plan that says, okay, I'll be there 99 chances out of 100. People say, you have 1% are you crazy? No, you cannot put that in written. You cannot plan that. So what they do is they plan a flight together where the probability of running out of fuel is extremely small. Okay? And so we're talking about the same thing. They plan for a stable equilibrium that you're not going to reach with guarantee, in the worst case framework, but with sufficiently high a probability that you don't have to worry about it. Okay? And at takeoff, the probability of getting to New York might be 0.99, not 1, or not 0.999999999. But of course, most of the time, it works. And what does it mean? It means that as you fly towards Gander, you make progress. And then as progress happens, the probabilities of your arriving in New York with the proper, the proper value, with enough nines after the 0, goes up. And then up, okay? And then when time comes to decide, should I go to Gander or should I replan? You usually replan. And then you replan because now you're legal to go to New York because you have a probability of 0.999999999 to get there. Okay? So the original plan is to go to the safe spot, and then you replan in order to get to your destination. Okay, so it's possible to do this thing in a probabilistic framework quite easily. New developments. I have a number of students, they're interested in aero stuff. And you know, there are lots of things that you can do flying stuff around. And one of the students, the one wearing the traditional attire, the F-15 pilot, said, I want to do formation flight. She's a 737 pilot as well, so she knows. I said, you're going to do formation flight, but we're not going to look at the formation flight per se. First of all, the problem has been worked on. It's been worked on by Lockheed, it's been worked on by Boeing, it's been worked on by Airbus. Okay, this is the Boeing experiment. Yeah, a couple of F-18s flying formation using a mix of their own work and work done by Jason Spire at UCLA. And the experiment was successful enough that it made the news in the French national newspaper. So I took a copy of it and I sent it to Jason. I said, Jason, you've made it to the French newspapers. Now this is a real thing. And Airbus did it with this thing named Fellowfly. Okay, it's more recent. Lockheed and others have done it also with military transport. Okay, and the whole purpose is always to save on fuel, right? Because when you fly in the vortex sheets or the vortex, the wake vortex of the other aircraft, you get from free uplift. Okay, so so I said, you're not going to work on formation flight. You're going to work on deformation flight, which is what is it that you're going to do if, say, that aircraft craps out? What should this one do? And of course, this is easy, but now, how about if this aircraft craps out and you have all of them here? What do you do? Okay, how do you disband in an orderly fashion? So that's what she's doing now, you know, trying to work on plan B. So I made my new saying, if it ain't being, I ain't flying. You know where this comes from? You probably do. No? There was this old saying about Boeing. People said, if it ain't Boeing, I ain't flying. Because Boeing aircraft had such a reputation for reliability. Okay, so it was another failed attempt on my part. But I am outside the aerospace domain. This is my boat. I'm very proud of it. Or her, sorry. It's 42 feet. It's ocean-worthy. It has everything. And by the way, this place, which is beautiful, is not so far away from here. It's Cambridge, Maryland. You know, there are spots about an hour away from here that are in the middle of nowhere. And that's one of them. So this is a Seaworthy Boat. It was made in Taiwan, probably made it by its own means to America. Okay, it's a boat made for ocean stuff. Okay, there is plan B everywhere. You see this guy here? That's the life raft. So depending on how far from the coastline you go, you can buy a big life raft or a small life raft. Okay? And the right thing to do is to buy the big life raft, even if you stay close to the coastline, because they're always smaller than they should be. Okay? There is this, okay, that's plan B in case you fall in the water. okay, together with a bunch of other stuff. That's this anchor is plan B, in case the main anchor fails. Okay, so there's plan B everywhere. And then 2 weeks ago, a guy showed up, a senior guy, very senior, like 75. And he told me, oh, I am with the Coast Guard Auxiliary. Oh, no, what's going to happen? You know, it's going to be a Coast Guard inspection. He said, oh, yeah, but I'm an old guy. You know, we're doing this as a service. We're volunteers and everything. And I say, okay, come on board and let's see. And sure enough, you know, for Plan B specialists, what happened? Okay, I had no visual distress signals, you know, the flares, okay, which is why you should never try and sail on the 4th of July, because people may just clap their hands when they use that. Okay, or the fire extinguishers, yes, they were there, but they actually totally expired. And besides the ones I had, he told me, oh, these are subject to recall because if you pull on the plug, they explode on your face. And then it went on. So this is about pollution. But he said, you should have a book with the navigation rules. So I said, what navigation rules? And I said, oh, that's where I could find everything I should know about what those different light patterns on the boats should be. And I was thinking, well, for a guy who talks about Plan B, this is not exactly a perfect record, okay? But I'm not the only one. What do you see here? Traffic everywhere, right? Including the emergency lane, all right? So the emergency lane is supposed to be for Plan B, right? It's for you to pull off in case you have a problem. Okay, out the window, all right? We're throwing it off. I mean, we get more capacity. Forget about safety, in some sense, right? So no Plan B. Okay, how about this one? Pandemic disarmament. Why France was ready for COVID-19 a decade too soon? They had all the stuff. They had like 3 billion masks ready, but did not maintain the thing. So they threw them away, and then there was 100 million left when the pandemic started, okay? So they just threw away the Plan B, okay? And so on and so forth. So, you know, there's a lot of stuff that can be done from here. I already talked about formation flight. Plan B means it's going to cost you. It's going to cost you in terms of hardware or in terms of capacity. You remember, like defensive driving? What's defensive driving? Let's see. Who knows about defensive driving?
Learn to steer away from problems.
So always steer away from problems, right? When you're on the highway, always make sure you have a certain distance between you and the car in front of you. And by the way, if you're being like tailgated by the guy behind you, make even more distance, because you're not going to be able to brake really hard, because for fear that the guy from the back will rear-end you. And even if the guy in the back rear-ends you and it's his fault, okay, it's still going to hurt a lot, okay? So that costs in capacity, right? You have to space out the cars. You have to space out the cars. But if you space out the cars, then rho goes down. And I'm sorry, but, you know, the flow rate is still rho times v, the speed, right? So rho goes down, even at the same speed, you don't have as much capacity. So these are interesting questions to ask as well. And then I was already alluding to that when I was talking about the Minotaur, but there is all sorts of similar problems applying at all scales of the system, whether it is at the scale of the navigation of the system or if you go lower and lower into like different software layers in order to design high reliability systems that don't fail. All right? So thank you very much. And I'm running completely over time, I see.
Thankfully, we're making some. Thank you, speaker.